Mr. Tarrou, in this math lesson, we are going to be introduced to finding multiplicative inverses of matrices, or finding inverse matrices. In this lesson, we're going to define what an identity matrix is. We're going to define what it means for two matrices to be inverses. And then we're going to go through a bunch of examples. The first one is finding the inverse of a 2 by 2 matrix. We're going to do that two different ways. The first way is going to just be using, our previous knowledge of how when you multiply inverses you get an answer of 1. So we're going to be finding an inverse of a 2 by 2 matrix using ultimately just the basic idea of multiplication, and then working with the elimination process to solve a two-system, two-variable, two-equation linear system. And then there is a quicker process or a streamlined process for finding the inverse of a 2 by 2 matrix, and we'll do an example using that process, and then at the end of that second example verify through what we see here in this definition that the inverse that we found actually indeed is. And then finding the inverse of a matrice, a square matrice bigger than just a 2 by 2 requires quite a bit more work. We're going to be setting up a 3 by 3 matrix and then using Gaussian elimination process and some directions that I give us to find the inverse of that 3 by 3 and then verifying that the inverse that we found really is an inverse of the original matrix. And then for our last example, we're going to be solving a 3-equation, 3-variable linear system by writing it into a matrix equation and then using an inverse matrix that I give you, solve for the 3 variables. Okay, so let's get started. The multiplicative identity matrix, a square matrix with ones down the long diagonal from the upper left-hand corner to the lower right. Okay, so we have these ones going from upper left to bottom right-hand corner, and then all of the other elements of the square matrix are going to be equal to 0. So we have a 2 by 2 identity matrix, and we have here a 3 by 3 identity matrix, and we are looking at it specifically. It must specifically be a square matrix. So if I wanted to just do I sub 4, that would be 4 columns, except I just went down, right? 4 rows and 4 columns with a bunch of ones. Definition of the multiplicative inverse of a square matrix. Again, we're talking about inverses of square matrices. Why we keep saying that a matrix has to be square, I'll get to that in a minute. Let A be an n by n matrix if there exists another n by n, another square matrix, and we're using the same variable, so it has to be the same size. A matrix inverse of A, or A to the negative 1 power, if you will, except that's not really just supposed to be flipping it, making it over, under 1, like 2 to the negative 1 is 1 over 2. It's a math function in terms of, that explains about inverse, such that matrix A times the inverse of matrix A is equal to an identity matrix. Notice the subscript on that identity matrix is the same as the original two matrices, the original matrix, and what we now is going to verify is the inverse matrix. And then A to the negative 1 power, or the inverse of A, times matrix A is again that same identity matrix. We're going from the upper left-hand corner to the bottom right-hand corner is all ones and everything else is zeros. From our previous lesson dealing with matrix operations, we learned that the multiplication of matrices is not a commutative process. Even if the matrices are the same order, same size, with the same number of rows and column. We understand that when you take a matrix and multiply it by another matrix, the number of columns in the first matrix has to match up with the number of rows in the second matrix. Well, okay, so then, we can multiply matrices together that aren't square, but to have this idea of an multiplicative inverse or an inverse matrix, we need to be able to take the original and what we believe is the inverse matrix and multiply it in both directions. Well, again, in general, multiplication is not commutative, so we aren't normally going to get the same answer when we change the order. And if they're not square matrices, you might have two matrices that you can multiply together, but when you change the order, not only could you get, and usually we'll get a different answer, but could very well be possible if they're not square matrices, you won't be able to multiply them together. So that idea of it being a square matrix is really important for these definitions of identity and inverse matrices. Okay, so let's get to our first example. Bam! First example, find the multiplicative inverse. Did I really teach you anything? All I did was show you, hey, this is the definition of identity matrix, and this is how you check for the two matrices are inverses of each other. So how am I supposed to find the multiplicative inverse? You know, I haven't got to the part of the lesson where I show you how to find the inverse of a 2 by 2 matrix. And that formula, basically, that I'm going to show you for finding the inverse of a 2 by 2 matrix is fantastic if you remember it. So if it's weeks, you know, down the road in your class, or just another class, or final exam, or whatever, and you get to a question like this and you don't remember the formula that I'm going to give you in a few minutes, well, what are you going to do? You're going to remember that in, you know, just basic arithmetic, when you multiply inverses, you get an answer of basically 1, the identity for multiplication. And with matrices, that means you get sort of the equivalent idea of an identity matrix. So this 2 by 2 matrix, again it's square, has to get multiplied by another square matrix of the same order. And when you multiply those two inverse matrices, you're supposed to get an answer which is the identity matrix. So another 2 by 2 matrix, only now that diagonal row is all ones and every other element in your matrix is equal to 0. Okay, well, sorry about the static. I'm having a hard time with that today. Don't know why. I've tried different channels on my wireless mic. But we're just going to multiply these together, using those matrix operations that we just learned about in our last lesson, and also use the idea or understanding of what it means for two matrices to be equal, which is that they're the same order or size, and all their corresponding elements are equal. And that's going to set up our linear systems that we'll have to solve to finish this problem out. So we're taking these matrices, and we're going to make sure, of course, this is kind of academic because I've made these square matrices the same order or size, but the number of columns in the first matrix has to match the number of rows in the second matrix, just to remind you of that. And we're going to get another 2 by 2 matrix. Okay, so the first row, first column. First row, first column. Negative 5w and negative 2y, or plus a negative 2y. And now we're going to take a look at the second row, first column. So second row, first column, we got 4w and 2y. Now getting on to the first row and second column, we have negative 5x and negative 2z, or you can write plus a negative 2z. And now we're looking at the second row, second column, so we have 4x and 2z. Okay, now that is going to need to be equal to the identity matrix of 1, 0, 0, 1. And let me just make sure I haven't done something silly here, because I'd hate to work all this out and realize that I've made a mistake. Okay, I have not, except for I forgot my square bracket. Okay, now if this 2 by 2 matrix is equal to this 2 by 2 matrix, then all the corresponding elements have to be equal by definition of what it means for two matrices to be equal. So first row, first column, first row, first column, we have 5w, negative 5w minus 2y has to be equal to 1, and we have 4w plus 2y has to equal 0. We have that negative 5x minus 2z has to be equal to 0, and 4x plus 2z has to be equal to 1. Excellent. Now, we've got, basically a linear system with two we have a linear equation with two variables, and we have another linear equation with two variables. So we're looking at two equations and two unknowns. We learned how to solve that using substitution or the linear combination or elimination process in Algebra 1. So that's what we're going to do here. We're going to find out what W and Y are. Now, it sounds like we're finding the intersection of two lines, and I guess really kind of we sort of are, but let's not forget we're looking for W and Y and X and Z that fill up this 2 by 2 matrix. We're trying to find that inverse matrix or matrix. So we're going to add these. Now, why am I doing a linear combination or the elimination process? Because instead of substitution, well, substitution would be horrible here because we don't have any coefficients of 1, and that would make fractions that we might have to carry through the whole rest of the solving of the systems process. Plus, we have coefficients which are already negative. So when we add those, we're going to get 0, effectively canceling out the variable of y. So we have negative 5 plus 4, which is negative 1w is equal to 1. We're going to divide both sides by negative 1. And I'm running out of room, so let's just bring it up here. W is equal to negative 1. Now, I know what W is. Let's plug that back into one of these original, if you will, linear equations. The one that seems like would be the easiest to work with is the bottom one. And we get 4 times negative 1 is equal to 2y, or excuse me, plus 2y is equal to 0. We have negative 4 plus 2y. Add both sides by 4 to undo that subtraction of 4 that's over here with the y. And now we're going to undo that multiplication of 2 with the y with division and get y is equal to 2. So now we know what W is. We know what y is equal to. Let's turn our attention. Let's pick a different color and work with this other system of equations. Again, we have a negative 2 and positive 2. So using the elimination process or linear combination process is a natural fit here. Negative 2 plus 2 is 0, canceling out effectively the z's, and we have negative x is equal to 1. Seems like I'm getting the same answers I had over there, but that's not going to be the case here, and not usually the case of getting the exact same pair of numbers. Divide both sides by negative 1, and we get x is equal to negative 1. Now, taking that value of x and plugging it into one of these original equations. Again, the second one here has less negative, so 4 times negative 1 plus 2z, I don't know why I'm writing that so funny, is equal to 1. We have negative 4 plus 2z is equal to 1. Now we're going to add both sides of this equation by 4 to undo the subtraction of 4 and get 2z is equal to 5. Undo that multiplication of 2 with division, and we get z is equal to 5 over 2. So our inverse matrix, the inverse of matrix A, is going to be equal to, let's see here, W is first row, first column, and that was negative 1. Then we have Y in the second row, first column, which is 2. The X is in the first row, second column, so right there, negative 1. And then finally Z is 5 halves. And that, excuse the static, I'm going to have to take that out. Now that is our inverse matrix. Now in our next example, we're going to find an inverse matrix, and we're going to do that A times inverse of A and the inverse of A times matrix A and check that this actually is the inverse. But that's, I don't want to do that with every example just because of the time that it takes in this lesson. But we should always verify that that actually is indeed the inverse, and we'll do that in our next example, finding inverse matrices. Or the inverse of a 2 by 2 matrix, given a process to follow, as opposed to just, actually I kind of like this better, just using our understanding of how mathematics works and how when you multiply two numbers which are inverses, you get that identity. All right, but there is a formula for finding inverses of 2 by 2s. Let's look at it right now. Bam! Multiplicative inverse of a 2 by 2 matrix. If matrix A is defined with these variables of A, B, C, D in row 1 and row 2, then the inverse of matrix A is equal to 1 over A times D minus B times C times the matrix where we have D, negative B, negative C, A. So what we're doing here is we're going to take this sort of downward to the right diagonal, multiply these values together, A times D, and then subtract that with the multiplication of the diagonal going in the opposite direction, B times C, and that's going to get some kind of scalar multiple. And then we're going to sort of change the sign and the position of some of these elements, A and D, the down to the right diagonal, they're just going to change position. So you see that D is in the bottom right hand corner, but now it's in the upper left, and A is where D used to be. And we're going to take these elements of B and C and simply change the sign. Yeah, and if matrix A is invertible, if it has an inverse, it is invertible if and only if A times D minus B times C is not equal to 0, because that is in this denominator. It's 1 over whatever that new value is from the product and subtraction. If A times D minus B times C is equal to 0, then A does not have a multiplicative inverse. So not every square matrix has an inverse. Okay, I'm going to cheat a little bit. We're going to use the exact same 2 by 2 matrix that we used in the previous example. And I'm going to tell you, I teach math, but I teach 4 different subjects at my high school, remedial math class, and then pre-calculus and AP calculus and AP statistics. And though I teach math and I love math, my memory is not that great, it doesn't seem at times, and I'm not going to remember this formula when I get around to teaching matrices the next year, if not unless I've used it throughout the entire year. That's why I like the first way I showed you how to find the inverse of this matrix, because I just had to understand that when I multiply 2 inverses, I get an answer of effectively 1. This is nice, but if you don't remember this, if you mess up the signs, if you don't reposition these elements correctly, or somehow get this messed up somehow, you're going to get the wrong answer. But it is nice when you remember it, so let's do that. We're going to have the inverse of matrix A is equal to 1 over, okay, now let's see here, A and D. Take those elements in that down to the right diagonal, and we're going to do negative 5 times 2 minus B times C. So we're going to do minus, let's see here, 4. It doesn't matter because multiplication is commutative. I can put the 4 first or the negative 2 first. I'm going to do, let's do top to bottom if you will. So negative 2 times 4. It's always a really good idea to use parentheses when you substitute, so I have that minus there that is in the pre-existing formula and the negative that I'm bringing in from the element of negative 2 times, this is going to become again that scalar multiple. Change the position of D and A, so what was in the bottom right hand corner is going to become the element in the upper right hand corner, and negative 5 is going to come down here, and then change the signs of the value, the element that's labeled with C, or that second row first column. So instead of 4 we have negative 4, and instead of 2, negative 2, we're going to change that sign and make it positive 2. Okay, so let's see what we get here. Negative 5 times 2 is negative 10. Negative 2, well, I guess just write that. Except I'm going to run out of space. Let me do a little bit of scratch work here that I'll erase. I'll put over here. Negative 5 times 2 is negative 10. Negative 2 times 4 is negative 8. So minus negative 8 might have probably been a good idea to go, oh, a negative times negative is positive, and just have that be, negative 10 plus 8. So we have 1 over negative 2 times, now this idea that A times D minus B times C is not equal to 0. We did not get an answer of 0, so we're not dividing by 0, thus making this inverse undefined or non-existent. And that's going to get multiplied to 2, negative 4, 2, negative 5. And when we multiply that together, applying that scalar multiple to each of these elements, 2 divided by negative 2 is negative 1. And again, 2 divided by negative 2 is negative 1, or times negative 1/2. Negative 4 times negative 1/2 is going to be positive 2. And then our last element is 5 over 2. So you see that we got the same answer, I would hope that we would, that we did in our previous example, working this, finding this inverse, just understanding the basic idea of multiplication and inverses that we learned quite a while ago, actually. Now let's actually make sure that this is the inverse. Now for the just purposes of the video and understanding that we've already learned how to multiply matrices, I'm going to step off and reveal over here one step at a time, taking matrix A and multiplying it by the, well, let's try that again. I'm going to take matrix A, not the one with all the variables in it, and multiply it by the inverse of matrix A in both directions, A times matrix A, inverse of A, and inverse of A times matrix A, and make sure that both times we get the identity matrix, and then move on to finding inverses of 3 by 3 matrices.